Hello, good morning, everyone. Welcome to today's webinar where we'll be taking a look at interactive display cabling and related problems. My name is Ryan Paragus and I'll be your moderator today, and James Lane will be your presenter. Before we begin, I do want to go over a couple of housekeeping items. Firstly, all attendees' microphones are muted, so if you'd like to ask a question, please either use the Q&A button or the chat window in your Zoom meeting client. Those questions may be answered during the flow of the presentation, or they may be held and answered at the end during our Q&A period. With that said, I'll hand it over to you, James.
Thank you, Ryan. Good morning, all. I am James Lane. I will be today's presenter. Today, we're going to take a look at Smartboard interactive display cabling basics. We're going to have a close look at video and USB cables. Then we're going to take a look at some cable management considerations. We'll wrap it all up in a summary and have a Q&A period at the end of the session. So for the basics, a standard Smartboard interactive display consists of a computer, the interactive display, a video signal cable, and a touch system data cable. Throughout this presentation, we're going to take a closer look at the cables that exist between the computer and the interactive display. The presentation is structured to answer several questions. What impacts these signal connections? What has changed with the cables over the last 20 or so years? Why appropriate cable choices and good cable management are important, and how to get the best performance and reliability from your system's overall connections. So to start with, we're going to look at one of the why questions, and that is the impact of poor signal connections. If you have a poor signal between your computer and your Smartboard display when using analog videos such as VGA, you're going to see grainy, fuzzy, noisy, oddly shaped, or otherwise difficult to see image on the display. Images may also appear duplicated or ghosted, or they may be discolored. Perhaps they're a little more red than they should be, or a little more blue than they should be. I'm sure we've all seen this in the past with older televisions that get snowy and things like that. That's a typical analog video poor signal quality. Now, when using digital video, such as DisplayPort or HDMI, you get different behaviors. Poor signal quality can result in intermittent communication, where you'll see frames drop or the video pause for a few moments, or a complete loss of signal. In this case, the display may completely turn black and display no content, or the display might report that it's not receiving a signal or attempting to connect. Now, the reason that occurs is due to signal losses in cables. Transmission of electrical signals are impacted by a lot of different things, including natural attenuation. This is a property of physics, where the strength of the signal reduces in intensity as it transmits through a medium, a wire, and so forth. The frequency of the communication signal and the timing of that communication signal are also impacting the electrical signals. Higher frequency signals are commonly used for faster data transfer. Higher frequency signals require tighter signal timing and are also more affected by signal attenuation. Low frequency signals, such as a 60 hertz or 50 hertz mains power signal, can travel much farther than high frequency signals in the megahertz or gigahertz range. In addition, the overall connection resistance and capacitance. Every electrical circuit has properties known as resistance and capacitance. And the wire that's used in a cable, depending upon the type of metals in the wire and how it's constructed, will have either higher or lower resistance and capacitance. And the type of terminators used at the ends of the cables and in the connected equipment also impact this. Obviously, the lower the overall resistance and capacitance, the longer the signal can be transmitted. Electromagnetic interference is also a factor that affects electrical signals. as electricity passes through the wires in a cable, it both produces and is susceptible to electromagnetic interference, which comes from outside the cable over radio waves and things like that. So good shielding in a cable helps to reduce both transmitted and received electromagnetic interference. We'll take a little more look at some of the ways that cables do this in later slides. So with a standard display, there's a bunch of common cable considerations. The length and quality of the cable, the routing and movement of a cable, additional connection points such as wall outlets and extenders, signal converters, repeaters, and active extenders. These are all common things that typically exist between a computer and a smartboard interactive display, which can either positively or negatively impact the signal. We're going to take a closer look at each of those in later slides. It's important to note that newer computer equipment and smartboard interactive displays now support higher image resolutions and more features and functions than older models. Therefore, the connection cables need to handle more data, higher bandwidth data than cables used with previous models. Therefore, the tolerances for the 4 points we mentioned above become more important with newer equipment. Now, Smart's covered a lot of this in the documentation that's available for each of our products. Every product model Smart sells has several documents associated with it. The product specification document, the installation and maintenance guide, and a textless installation guide that comes in the box. And all of these include guidelines for best practice for installing the connection cables between computers and the smart equipment. It's important to note, however, that different product models will have different requirements, usually around recommendations for maximum cable lengths, and in some cases, different installation guidelines. So it's important to pay attention to each model's guidelines. Back in 2016, Smart also published a general purpose document that is not specific to one model of Smart product, but is more generic and applicable to all equipment, whether it be smart displays or other equipment that you use in your schools and businesses. This is the installation best practices for smart products, and it is available at this URL. What we're going to cover today expands on features that are already talked about in that installation best practices, and we're going to start this section taking a closer look at video cables specifically. We're going to look at what they do and how they're constructed. Now, as I go through this presentation, it's important to note that a cable is simply a group of wires inside a rubber or plastic coating. So a cable does not refer to one wire, it refers to a group of wires all in one cohesive group. Throughout history, there have been many different video signals used with smart equipment. In the past 20 or so years, we've seen analog video such as composite, S-video, component video, and VGA, mostly associated with the older front projection whiteboards and projectors. And we also have digital video, DVI, HDMI, and DisplayPort, which are associated with common interactive flat panel displays. It's important to note that through all of these, none of the only ones which these all carry video signals, but HDMI and DVI also carry audio and other signals. The previous analog cables did not carry audio, so you needed separate wiring for audio. We're not going to go into the audio wiring in this presentation. Of note, the maximum resolution that the cables are good for has increased over time. The older composite and S-video cables were typically used for up to about 480 standard definition resolution displays, which was about 720 by 480 resolution. High quality analog cables can carry higher resolution video signals. So it's not a hard limit, but you do see more signal degradation and poorer video quality if you try to push higher video signals. Same with composite. Composite was great for high definition or 720p which was a resolution of about 1280 by 720. And then when we reached VGA, it was typically used for full high definition, 1080, which is 1920 by 1080 resolution. Yes, you can drive higher resolutions through VGA, but for the most part, for good picture quality, 1080 was the typical commonly used limit. When we get into digital video, this is where we start to see much higher image resolutions. DVI has different operating modes, single link and dual link. And when used in dual link mode, you could get a really high resolution, which is similar to today's 4K displays, 3840 by 2400. This is what was called the wide quad ultra XGA resolution. That's where that cable tops out though. HDMI and DVI start supporting around full high definition, 1920 by 1080, and go well beyond that, even up to 8K displays today, and who knows what the future holds for these cables. The primary difference with HDMI and DisplayPort, however, is that they come in multiple different versions. And we'll talk about that specifically for HDMI in a later slide. Newer versions obviously support higher resolutions than older versions. So as an example, here's a list of common resolutions from standard definition all the way through to 4K ultra high definition. The common name, if you're thinking about television naming, is 240p, 720p, 1440p, etc. And what that usually refers to is the number of vertical pixels in the display. A standard definition 480p signal, for example, was a 640 by 480 resolution image. As we get higher and higher, all the way up to 4K ultra high definition, 3840 by 2160 pixels. If we multiply that out, we have a change over the last 20 years from roughly 100,000 pixels per video frame up to 8.3 million pixels per video frame. And you'll notice that it increases more than just a little bit per frame. The jump from 480p to 720p is a threefold jump. The jump from quad high definition, or sorry, let's take a look at full high definition because this is what most people use. It's about 2 megapixels. 4K is 4 times that at 8 megapixels roughly. And that's per frame. So if you're looking at 60 frames per second, that's a lot of pixels that have to go through the wire. The older analog cables, here is a breakdown of a composite video cable. It was basically 2 wires, one central conductor, one return wire in the form of a coaxial cable. Coaxial means that the central wire is in a core surrounded by a dielectric spacing and surrounded by a shield with the return wire being the braided shield on the outside. Coaxial cables are great for reducing electromagnetic interference and increasing the maximum length a cable can do, especially at higher frequencies. When we went to analog video, a lot more wires get put in that cable. For example, each individual color, red, green, and blue, has its own 2 wires for that color, and then there's additional wires for control signals and connection, disconnections, etc. This particular illustration shows a very high quality VGA cable, which is using mini coaxial for the high frequency color signals and regular wires for the remainder of the VGA construction. When we get to digital cables like HDMI, there's even more wires constructed in a more specific fashion. HDMI, this is a standard HDMI cable with 3 wires, a twisted pair for the signal, and a return ground wire, all within a shield. And there's 5 sets of that. And then there's 4 individual wires for command and control systems and a shield ground return wire. You'll notice that the construction of these wires, the twisted wire groups that are data communication channels, are individually shielded, but the entire cable has another electromagnetic shield around it as well. So the complexity of cable construction has increased as we move from analog to digital. But that's not the end of the story. What you saw was a standard HDMI cable. The HDMI protocols have changed over the years. There's been from 2002 through 2017, HDMI has gone from version 1 to version 2. The features and capabilities of HDMI have increased. The maximum resolution that it supports, the number of audio channels it supports, additional features such as high dynamic range lighting, higher bit depths for wider color gamuts, and things like that increase as the version increases. There's some great resources online at the hdmi.org website. Wikipedia has a nice article that really goes into the details if anyone wants to know. But for our purposes, we're looking at the bandwidth the cable can handle. A typical HDMI cable for standard HDMI cable is good for about 5 gigabits per second of data transfer. High-speed HDMI cables are good for about 10 gigabits per second data transfer. Today, with the HDMI 2.0 and 2.1, there are premium high-speed and ultra high-speed cables, which are rated for 18 gigabits per second or 48 gigabits per second. These specifications came out in the years indicated on the left, but products using those specifications usually show up 2 to 3 years after the specifications ratified. We're now in 2021. We are starting to see HDMI 2.1 products on the market. Smart knows that a lot of schools and businesses do not buy the newest stuff right away. So all of our displays do not require a 48 gigabits per second ultra high speed HDMI cable. They only need a premium high speed HDMI cable rated for 18 gigabits per second. That still gives you a good 4K 60 hertz refresh rate display and all of the audio that's necessary for a typical smart system. The features in HDMI 2.1, you can have up to 8K video and things like that. That's more for cinema, especially with the multi-channel audio, surround sound systems, etc. Doesn't really apply to today's smartboards. Today's smartboards are more focused on HDMI 2.0. Now, I want to point out that the hdmi.org website, the HDMI organization, has a web page that is specific to the cables. They certify specific cables for premium high speed or ultra high speed. There was no certification for the older high speed or standard cables. So when you're looking at HDMI cables, Smart strongly recommends that you get a certified premium high speed HDMI cable. These typically come with this label, a QR code to validate the certification from the HDMI.org website. And there is a list of common cable manufacturers that participate in the certification program for anyone who's interested. So back to our presentation. Let's take a look now at USB data cables because they've also evolved over the years. Just like HDMI, USB has gone through several versions over the years, and each of those versions has an increase in data bandwidth that the cable needs to accommodate. USB 2.0 high speed is good for about 480 megabits per second, and that's fantastic for multi-touch interactive displays and a few peripherals like keyboards, mice, and low-resolution webcams. When we get into a need for adding video over this, high-resolution webcams or DisplayPort alternate mode, things like that, we need faster stuff. So we get into the USB 3.2 Gen 1, which used to be called USB 3.0 or USB 3.1 Gen 1, which is a super speed USB cable. That's capable of 5 gigabits per second, almost 10 times the bandwidth of the older high-speed USB 2.0 cables. There are also newer USB technologies with even higher data bandwidth. We don't need those for the Smartboard interactive display systems because we're not using things that require excessive amounts of bandwidths. But it's important to be aware that these ratings exist. And the USB Implementers Forum provides guidelines for how cables are labeled, if they're labeled for super speed, if they're labeled for high speed, if they're labeled for carrying 10 gigabits or 20 gigabits per second of data. The cables themselves have gone through a lot of changes. USB 2.0 Type A and Type B connectors typically had about 4 electrical contacts on the connector, 4 wires in the cable. USB 3 added additional wires. There were 9 wires in the cables. Today's USB Type C cables use 24 connectors, so there's a lot more wires in the cables. If we have a look, here's a typical USB 2.0 cable construction. It consists of a twisted pair. Twisting is a great way to reduce interference in high frequency cables, short of using mini coax. It's cheaper than mini coax and almost as effective. And a couple of power cables. When you switched to USB 3, you'll notice that there were an additional 2 sets of twisted pairs, an additional 4 wires for the USB 3 data. Now, when we get into USB 3.1, which is now called USB 3.2 Gen 2, there's a lot more wires in the cable. And they switched from using twisted pairs to using mini coax to handle higher frequency data. It's important to note that as we get into higher frequency data, larger bandwidths, the lengths of the cables gets reduced. And this is because of the properties we discussed earlier, attenuation being the main one. So for USB 2.0, the USB Implementers Forum recommends that USB 2.0 with Type A and B connectors really shouldn't be longer than about 5 meters or 16 feet. Once we get into the newer USB cables with Type C connectors, the maximum cable lengths is reduced further. For USB 2.0 data, 4 meters. For USB 3.2 Gen 1, which used to be called USB 3.0, 2 meters. For USB 3.2 Gen 2, 1 meter. And future USB, like USB 4, is going to be even shorter to handle the higher data bandwidth. We looked at HDMI cables a few slides back. The HDMI forum does not specify maximum recommended cable lengths in the same way that the USB forum does. So it's a little more difficult to identify your maximum appropriate cable lengths for HDMI. Smart typically recommends 7 meters or less for HDMI when you're using 1080p or 4K at 30 hertz refresh rate. If you're using higher resolution images, 4K 60, etc., shorter cables are recommended. And of course, that depends heavily on the cable itself, how it's manufactured, the quality of the materials within it, and so forth. Higher quality cables will obviously have better properties for resistance, capacitance, and attenuation, which means the signal can travel farther. So to summarize, newer video and USB cables contain more internal wires than previous versions, and they are assembled in more specific and complex ways in order to support the higher data bandwidth needs of today's newer data protocols. The individual wires are also generally thinner than previous versions. If you've noticed, if you've looked at any cables in your school or organization over the years, the thickness of the outer diameter of the cable really hasn't changed all that much. So in order to accommodate more wires internally, the wires necessarily have to be thinner and smaller. And the higher data bandwidth requirements of newer video and USB result in shorter cable length limitations for reliable operation. So now I'm going to take a look at the tips and tricks around cable management. We're going to take a look at some common cable damage causes and how to avoid them. And we're going to show you some cable management practices which can impact the operation and longevity of your signal connection cables. One of the most common causes of cable damage is compression. Compression is where the outer jacket of a cable is squeezed so hard that the internal wiring structure gets damaged. Either the electromagnetic shielding has a gap in it, allowing electromagnetic interference, or the wires inside are physically damaged. On the left, you'll see photos of good and bad cable tie use, where the top photo shows no problem at all. It's holding a cable in place without issue. And the bottom shows a bundle of cables physically damaged because the cable tie was attached far too tightly. In addition, pinching cables between furniture, putting it on a floor where it can be rolled over by chair wheels, things like that, can also result in damage to the cables. If compression damage is really high, the wires inside can actually be severed or cut, and that could result in a complete loss of signal, not just a degradation. Another common way to damage a cable is by bending it too tightly. Cables, every cable in existence, whether it's used for HDMI, USB, industrial machinery, automotive wiring, whatever it's used for, has a minimum bend radius that the cable manufacturer specifies, beyond which the internal cable can be damaged. Now, a lot of manufacturers of cables don't publish the minimum bend radius on sales and marketing packaging. So if you are unable to find a minimum bend radius from a cable manufacturer, there is a general rule of thumb, which is 10 times the cable diameter. So if a cable is 6 millimeters or 1/4 inch in diameter, you really don't want to bend it sharper than a radius of about 60 millimeters or 2.4 inches approximately. At the bottom here, I've got a photo showing an example where the minimum bend radius was not adhered to, and you can clearly see that the cable is experiencing damage here. You can see something protruding upward in this part of the cable. That is a clear indication that there's damage to this cable. In addition, this one shows compression damage due to an over-tight tie. Very easy to avoid these just by including gentle bend radiuses and gentle grip with cable ties. Another common damage for connection cables is the connectors themselves. If connectors are mishandled or forced, then the connection pins can be damaged. The photo that you see here shows clearly this pin, and even this top pin up here are not in the right locations where they should be. They're bent out of shape, they're damaged. They're not going to make proper electrical contact when plugged in. So it's always important to be gentle when you're plugging in cables. If a cable does not go in easily and smoothly, do not force it, because if you force it, you end up risking cable damage. If there's already a little bit of damage, you just make it worse by forcing the cable. If it doesn't go in properly, take a closer look at the cable and the port on the device to make sure that everything is consistent, not damaged. Another cause of cable damage is repeated movement. Wires are designed to accommodate a certain amount of movement, but too much movement will break the internal wires. So when dealing with a situation where movement of a wire is required, such as a height adjustable wall mount, you want to make sure to minimize the amount of movement as much as possible. A good way to do that is with a service loop. I've got an illustration here that shows basically the range of height of a height adjustable wall mount that a display is on, and the display at the top of that range and at the bottom of that range. Now, what you'll notice here is that we've secured the cable in two places. One is in a fixed location on the wall or the mount. Another is in a fixed location on the display itself. And we have a loop of wire. It's a nice long loop going between those two fixed locations. When the display moves down, there's enough wire in that loop to allow a nice gentle curve without causing excessive strain on the cable, and no sharp bends, positioned in a way that it doesn't get pinched when the cables are moving. And the cable going into the display goes in at a nice straight angle with a gentle curve. No sharp bends. The weight of the cable is not pulling down on that connector. It's secured with a cable tie. And that's a good way to make sure that your cables last as long as possible. You know, from the fixed location, obviously from there it would go to whatever computer equipment you're using. Another recommendation is to avoid extra connection points. Extra connection points, such as a passive extension cable or a passive wall plate, add more connection points. They add resistance, they add capacitance to the overall connection cable, and that increases the risk of signal degradation or loss. It can reduce signal integrity, which can reduce the maximum end-to-end usable cable length, which is kind of the opposite that people want when they're using wall plates. They want to, you know, extend the connections. Unfortunately, the reality is that using these kinds of wall plates can actually reduce the maximum usable cable length. In addition, we talked about the growth and evolution of HDMI protocols from 1.0 to 2.1, and the fact that they have different data bandwidth requirements. The fact that the HDMI forum certifies premium and ultra high speed HDMI cables. This wall plate in this illustration, I have no idea what it's rated for. Is it rated for a 5 gigabit per second standard HDMI? Is it rated for 10 gigabits per second high-speed HDMI? Is it rated for 18 gigabits per second premium high-speed HDMI? I have no way to know that. And that can make it very difficult to know if your entire connection from your computer to your smartboard display is within specifications. Therefore, it's best to avoid these types of wall plates or extension. There are exceptions to that, and we will cover that in a future slide. In fact, that's this slide. So signal converters, repeaters, and active extensions can be quite useful. Signal converters change a signal from one type of protocol to a different one. An example of this is a DisplayPort to HDMI converter, which is quite common. Signal transceivers are signal converters which also change the media being used. These are also very common. A Wi-Fi access point is a good example of this because it changes a wired Ethernet network into a wireless network. In the case of extension cables, we'll get to that down here, but active extension cables, which include a repeater or a signal converter, can also include signal transceivers. Fiber optic extenders are an example of that. They convert HDMI on copper wire to a different protocol, usually proprietary based on the manufacturer of the extender, which uses light over fiber optic cable. Then at the other end, it converts it back to HDMI over copper. Repeaters are another thing. They receive a weak signal and then repeat it, being a stronger signal. An example of this is an active HDMI extension cable. Active cables typically require power to drive the internal electronics. Sometimes that power comes from the HDMI source, your computer, etc. But a lot of the higher end, higher quality ones use an external power adapter. There are some considerations with using signal converters, repeaters, and active extenders. The first is signal timing. Because a signal needs to travel from source to destination, and the timing of that is critical, timing can be negatively impacted when you're repeating, converting, or extending signals, and this can cause communication failures. For example, if an HDMI source asks the display, sends a signal to the display saying, hey, do you support high definition content protection? Yes or no? And the source waits for, say, 1/10 of a second for the answer. If that answer doesn't come within that wait period, then the source device won't know if the display supports high definition content protection, will probably assume that it doesn't, and may not send a signal. Other consideration: the more connection points you add to an overall communication chance, the higher the risk of failure and the higher the quantity of things that you need to check when troubleshooting. It's really easy to check one cable between your computer and your display. It's more difficult to check 2 or 3 cables, especially if they're installed inside a wall or conduit or other locations. More parts and more complexity usually result in higher cost. The active devices include electronic circuits to do what they do. Those electronic circuits increase the cost of the product. Sometimes it can be cheaper to use one high quality HDMI cable than a lower quality HDMI cable and an active extender. In addition, all parts in the communication chain need to support the same protocols. Say we have a high-speed HDMI extension cable, but you're trying to put a 4K 60 Hz video signal over it. 4K 60 Hz video requires premium high-speed HDMI cable. So even if your computer supports the 4K 60, your initial video cables is premium high-speed supporting the 4K 60, your display supports 4K 60, but you choose to use an extender that doesn't support 4K 60, you're not going to get 4K 60 out of that system. In addition, high definition content protection. High definition content protection requires that all parts in the communication chain all support high definition content protection. We took a look at a passive extender wall plates in a previous slide. Obviously, that doesn't support high definition content protection. It may carry the signal just fine, and it may work just fine. But if you use an active extension cable that doesn't support HDCP, or a video splitters typically do not support HDCP, then if the source is trying to transmit protected content, that protected content will not reach the display. When that happens, you usually get just a black screen. So to summarize today's webinar, when using connection cables between your computers and your Smartboard interactive displays, make sure that all of the cables are rated for the system's data speeds. Adhere to length limit recommendations, and if you're unsure of what the length limit recommendations are, use shorter cables where possible. Always avoid passive extension cables and extra connection points. Do not over tighten cable ties. Help your cables last longer. Avoid sharp bends. Pay attention to the minimum bend radius guidelines. Be gentle with connectors, and use service loops with plenty of slack to accommodate physical movement when needed.